Okay, let's talk about AI. You hear the terms all the time, right? Artificial intelligence, machine learning, deep learning. They're everywhere. But what do they really mean? And more importantly, how do they all fit together? It can feel like this big, confusing cloud of buzzwords. Well, today we're going to clear the air. We're going to break it all down and build a really clear picture, starting from the very beginning. To really get our heads around this, let's start with this classic definition. I think it just perfectly captures the huge ambition of this whole field. The goal here isn't just about writing clever code. It's about trying to recreate something that feels fundamentally human, intelligence. But that, of course, immediately brings up a massive question. What does it even mean for a machine to be intelligent in the first place? So here's our game plan. We're going to start with that big philosophical dream of intelligence. Then we'll see how that dream led to a huge shift towards teaching machines how to learn. We'll even peek under the hood at the neural networks that power pretty much all of modern AI. After that, we'll look at a whole toolbox of different AI models, and we'll wrap up by asking, what does the future of all this learning really look like? All right, part one, the dream of intelligence. See, long before we had super powerful computers, we had some really powerful questions. The pioneers in this field were really wrestling with the nature of thought itself and what it would actually take to build it. And right from the get-go, the field's kind of split into two big camps. On one side, you've got what we call weak AI. This is all about results. If a program can beat a grandmaster at chess, who cares how it does it? It's showing intelligent behavior, and that's enough. But the strong AI camp would say, whoa, not so fast. For them, true intelligence means the machine should think like a human, not just get the same answer. It's kind of like the difference between building an airplane that flies versus building a mechanical bird that actually flaps its wings to fly. Two very different goals. So how in the world do you test something like that? Well, Alan Turing came up with this brilliant idea called the imitation game. It totally sidesteps the philosophical debate and just focuses on performance. Picture this. You're in a room typing questions to two mystery contestants. One is a person, one is a computer. If, after a while, you can't reliably tell which is which, well, the machine passes. For Turing, that was enough to say it was thinking. Early AI couldn't learn for itself, so it had to rely on rules written by humans. And these rules were called heuristics. Just think of it like a rule of thumb. When a doctor diagnoses an illness, they aren't running some perfect, rigid algorithm. They're using experience, these rules of thumb. If I see symptom A and symptom B, it's probably condition C. These first expert systems were basically just giant databases of these human-written rules. Now, that rule-based approach was a great start, but it had a massive, massive limitation. And that brings us to part two, this huge fundamental shift away from programming rules and towards learning from data. Yeah, exactly. I mean, think about trying to recognize a cat in a photo. Could you actually sit down and write a complete list of rules for what makes a cat a cat? You'd say, okay, pointy ears, whiskers, fur, but it gets complicated so fast. What if the cat is looking away? What if it's a weird breed? What if it's just a kitten? The list of rules would be literally infinite. This is where that old rule-based approach just completely falls apart. And this is where the solution comes in, machine learning. This is the big idea. Instead of trying to tell the computer the rules for finding a cat, we just show it, say, 1,000,000 pictures of cats. We just say, here, you figure out what the patterns are. The machine learns directly from all that data, and it comes up with its own rules that are way more complex and subtle than anything a person could ever program by hand. And you can use this learning approach to solve all sorts of problems. For instance, if you want to predict a specific number, like what a stock price will be tomorrow, that's called regression. If you're trying to sort things into buckets, like deciding if an email is spam or not spam, that's classification. And what's really cool, if you just have a huge pile of data and you want to see if there are any natural groups in it without any labels, that's called clustering. Okay, so this leads us to the real engine behind modern AI. How does a machine actually do this? How does it learn such complicated patterns from just raw data? Well, the answer comes from an idea inspired by the most powerful computer we know, the human brain. And that is deep learning. It's a special kind of machine learning that uses what we call an artificial neural network. Now, the deep part, it just means the network has a lot of layers of these artificial neurons. And having more layers lets it learn way more complicated patterns. In the first few layers, it might learn to see simple things like edges or colors. But by the final layers, it's combining those to recognize complex things like faces or objects. So information just flows through this network like a cascade. Data comes in the first layer, and each little neuron does a quick calculation and decides what signal to pass on to the neurons in the next layer. And this chain reaction of really simple decisions allows the network as a whole to solve incredibly difficult problems.
But wait, how does it know what calculations to do? How does it get it right? Well, this is the real magic. It's called backpropagation. After the network makes a guess, let's say it looks at a picture of a cat and says dog, it compares that guess to the right answer. It sees how wrong it was, and then it sends a signal backwards through the network, tweaking all its internal connections just a tiny bit to be less wrong next time. It's a feedback loop. Guess, check the error, adjust. And it does this millions of times.
So even though the machine is learning by itself, a data scientist is still in charge of setting up the initial conditions. These are called hyperparameters, and you can think of them as all the dials and knobs on the machine, things like how many layers to use or how fast it should learn. You have to tune these knobs just right to get the best performance.
Okay, so now we get the basic idea behind the engine. But here's the thing. Not all neural networks are built the same. So let's take a quick look at a few different types, because each one is like a specialized tool designed for a very specific kind of job. First up, we've got CNNs, or convolutional neural networks. Honestly, just think of these as the eyes of AI. They are absolute masters of computer vision, specially built to find patterns in pixels. This makes them perfect for stuff like recognizing objects in a photo or analyzing medical scans. Then you have LSTMs. These act as the memory of AI. They're built from the ground up to understand sequences of data, like the words in a sentence or changes in the stock market over time. Their ability to remember what came before is absolutely critical for understanding the context in language. And then there's this one, which is just wild. Generative Adversarial Networks, or GANs. A GAN is actually two neural networks that are forced to compete against each other. You have the generator, think of it as an art counterfeiter, trying its best to create fake images that look totally real. And then you have the discriminator, that's the detective, trying to spot the fakes. As they battle it out, the counterfeiter gets better and better at making fakes, and the detective gets better and better at spotting them. And the result? You get an AI that is unbelievably good at creating brand new, totally realistic stuff from scratch.
So we've gone from the big philosophical ideas all the way down to the specific tools being used today. So for our last section, let's just take a quick look at what's coming next and why it's going to matter to all of us.
One of the most exciting areas right now is reinforcement learning. Now, unlike the other methods we talked about that learn from a fixed set of data, a reinforcement learning agent learns by doing. It's basically trial and error. Think of it like training a dog with treats. The agent takes an action in an environment, like moving a piece in a game of Go, and it gets either a reward or a penalty. And over millions and millions of tries, it figures out a strategy to get the most reward possible. This is exactly how systems like AlphaZero taught themselves to play games at a level no human could ever match.
And this brings us to the final and maybe the most important thought. These systems aren't just experiments in a lab anymore. They are incredibly powerful tools that are actively shaping our world. They're helping doctors, they're creating art, they're driving our economy. And as they get woven deeper into our lives, we are forced to ask some really profound questions about bias, about who's accountable when things go wrong, and about how this will change the very nature of work. The future of AI isn't just a technical challenge anymore, it's a human one.